All right, so we're moving on to section 3.1 today, which is quadratics. So a lot of this might be review from a 106 class or some other intermediate algebra class that you took. So suppose you were asked to graph this function, g of x equals x squared minus 2x minus 3. It's a parabola. Let's just graph it on the graphing calculator. Let's pretend we know nothing about what this looks like. We'll graph it on the calculator, see what we get. Oops. Okay, so x squared minus 2x minus 3. And I'm just going to do zoom 6, do a standard window, and I get this parabola. So what are some key points? If I was going to copy this drawing down, I was going to copy that graph onto the grid that I was given. What are some key points that I would want to make sure I got right? Yeah, Teddy? When x is 0, so that's the y-intercept. So it looks like I have a y-intercept at about -3. When y is 0, so my two x-intercepts looks like they're at -1 and 3. And then what other point would be important? Yeah, the minimum, this point right here, which looks like I could eyeball it. It looks like it's at 1, -4, but we could have the calculator do it exactly using the minimum command in the calculate menu. We just give a left bound and a right bound and a guess. And it does look like 1, -4. So those are sort of 4 important points: x-intercepts, y-intercept, and the minimum. Anybody remember from a previous class what that minimum is called in a parabola? The vertex. It could be a minimum or a maximum. So my important points are x-intercepts, which there could be 2 of. There could be 1 of, and there could be none. Y-intercept, there'll be 1 of those. And the vertex. So those are the important points for graphing a parabola. Intercepts and vertex. It will always hit the y-axis. Yep, it will always hit the y-axis, because no matter where you put the vertex, like if I put it way over here and it goes like that, right, this will go up. The domain is all real numbers for every quadratic function. So this will eventually move over here and cross the y-axis. It just might be like really far off our graph or out of our window. So we're going to use transformations to analyze a quadratic. So this might be a different approach than you used when you studied these the first time. So we're going to use the parent function f of x equals x squared and our knowledge of transformations to find another way to express a quadratic function. So this is one way, ax squared plus bx plus c. That's sort of the standard way we express anything quadratic. And then we're going to find another way that's sometimes called standard form, sometimes called vertex form, and we're going to use transformations to get there. So if I start with f of x equals x squared, which looks like We should know what it looks like from project 3. Looks like that. And if I was going to reflect or shrink or stretch it vertically, I would have to throw a number in front of the x squared, the a. That would give a vertical stretch or shrink depending on the value of a. So what value would a have to be in order to cause a reflection over the x-axis? Negative, yeah. A negative out front will cause that thing to flip. And what value of a would cause a stretch, vertical stretch? What kinds of a values? Multiplied, yeah, by what? What kind of number would I multiply by? Anything bigger than 1, good. And to get a compression, a would have to be like a half or anything smaller than 1, yeah. So what is my vertex of ax squared? If I multiply all the y values in x squared by some number a, what happens to the vertex? That point right there. What? It'll move where? Well, what are the coordinates of this point right now? 0, 0. If I multiply the y coordinate by something, it's going to still be 0, 0, right? So it actually stays right where it is. Because a vertical stretch just multiplies the y coordinate, and the y coordinate is already 0. When you multiply by 0, you still get 0. So my vertex is still going to be at 0, 0. Now, what if I wanted my new vertex to be located somewhere else in the coordinate plane? I want it to be at h comma k. Yeah. So I'm going to shift. Yeah, I'm going to shift it left or right by h and up or down by k. So I'm going to go like that. I'm going to subtract h from the x value to shift right h and add k on the outside to go up k. This is what we call the standard form or the vertex form of a quadratic. It's just another way of expressing ax squared plus bx plus c. But if we write it in a slightly different way, like this, now we can use everything that we know about transformations to help us analyze the graph. Oh, sorry, this has to be squared. So this is the standard form in the book, or vertex form. So your book calls this the vertex form. So if you're reading, I'm sorry, the standard form. So if you're reading your book, they refer to this as standard form. Like every other textbook in the world calls this vertex form. So I will try to say standard form, but I will probably slip up. So we're going to call this standard form or vertex form. Why do you think that most books call this a vertex form? Why that name? Yeah, because you can read the vertex right out of the equation. The vertex is at h comma k. So here's a quadratic function in standard form or vertex form. What information do we know right away about this quadratic function? I know it's vertex. Where is its vertex? It was originally at 0, 0, and it's going to shift how? You're on the right track. You're doing a transformation from 0, 0. What is this minus 3? It's in parentheses, right? So it's going to be a horizontal. And it's kind of like the opposite of what you think. Right 3 units. From 0, 0, right 3 units would land me at 3 for x. And up 5. So if I shift right 3 and up 5 from the point 0, 0, I land at 3, 5. So I know my vertex right away. So that's the advantage of the standard form or the vertex form. You can get the vertex just by glancing at it, if you know a little bit about transformations. So the vertex theorem, this is when the quadratic is given in the general quadratic form that we're used to, ax squared plus bx plus c, you can't just read the vertex right out of it, right? Like in the previous one, we could just take a quick glance and go, oh, the vertex is at 3, 5. But when you're given in this form, ax squared plus bx plus c, you can't read the vertex immediately. But there is a theorem that says that the vertex, the x-coordinate of the vertex, is at negative b over 2a. Does that seem familiar at all, negative b over 2a? It's part of the quadratic formula, and that's exactly where it comes from. I'm not going to do the whole derivation because you're never going to have to do the whole derivation, but know that it does come from somewhere. It's not just like a magical made-up number. So if I know the x-coordinate of the vertex is at negative b over 2a, how could I get the y-coordinate of the vertex? What do you mean? If you have an x value, like 2, and you have a formula, y equals something, how do you get y? I've heard a couple people say it really softly. Plug it in, yeah. You have the x value, and you have a formula that gives you y values. So we're just going to take this x value and plug it into f to get a y value. So if I knew that x was 2 and I wanted to know what is y when x is 2, I would just plug a 2 in here. So let's look at an example. We have a quadratic equation, a quadratic function written in the general form, the ax squared plus bx plus c. I want to switch it to the vertex form. I want to find its y-intercept, its vertex, its minimum value, and its x-intercept. So all those key things I want to try to find out about this. So y-intercept, anybody remember in general how you find a y-intercept? You got it, make x 0. So this is like test 1 material. Make x 0. So I make x 0, right? Because any y-intercept is going to be 0, something. So I make the x 0, and I would get 3 for y. And now the coordinates of my vertex would be negative b over 2a, gives me the x-coordinate. So negative b would be negative 4 over 2 times 1 is negative 2. That's the x-coordinate of my vertex, negative 2. To get the y-coordinate, I'm just going to take that negative 2 and plug it into the formula for f. So negative 2 squared is 4. 4 minus 8 is negative 4, plus 3 is negative 1. So my x-coordinate is negative 2. My y-coordinate is just f of negative 2, which is negative 1. So what's the minimum value of my function f? That's the vertex, that's the lowest point, right? But when I ask for minimum value, if you remember from other way, it's the y, yeah. When I ask for minimum value, they're asking for the y value of the minimum point. So minimum value of the function is -1, and it happens at -2. So if I was going to write this in the standard form or the vertex form, right, that looks like this. Where h and k are my vertex, and a is the same a in here, because this is ax squared plus bx plus c. The a's are the same. The coefficient on the x squared here is a 1, so that's going to be the a down here. So what is h in this case? -2. So I have x minus, then I have to write in my h, which is -2, and then plus k, which is -1. So if I just write it out a little simplified, I get y equals, I'm not going to write the 1 because 1 times, what? So I got 1 for a because there's an a in this form, the standard or vertex form, and there's an a in the general form, ax squared plus bx plus c, and they are the same number. They're always the same. So the a here was a 1, so it's a 1 in the other form too. So I'm not going to write 1 when I write out my final answer, because 1 times anything is just that thing. So I have x minus -2, that becomes x plus 2. And then plus -1 is -1. So what I just wrote here is equivalent, it says the exact same thing as this. X squared plus 4x plus 3. So let me just show you that. X plus 2 squared minus 1. When I square x plus 2, that's x plus 2 times x plus 2. So I FOIL, I get x squared plus 4x plus 4 minus 1 is x squared plus 4x plus 3, which is the formula we started with. So we just rewrote the general quadratic function in a different way. Kind of like you can rewrite 1 as 3 over 3, right? So we can rewrite a quadratic function in 2 different ways. Okay. Each one has its own advantages. Okay. The advantage of this one is that you can tell what the vertex is right away. What's an advantage of this one? What can you tell right away? The Y-intercept, great. And it's also easier to solve this thing for the X-intercepts. Because when you find X-intercepts, what do you do in general to find the X-intercepts of an equation? Make y 0. So we have 0, x squared plus 4x plus 3. So that can factor. So I get x plus 3 times x plus 1. So x ends up being -3 or -1. So if I was going to write them as points, it would be -3, 0, and -1, 0. Make the y's 0. Okay, so we'll do one more kind of thing together, and then I'm going to have you try some stuff. So I want to find an equation. So in the last example, we were given an equation. We were supposed to come up with all the properties it has, where is its vertex, where are its intercepts, etc. Now we have some properties. We have a vertex. It opens downwards, and it goes through the point 1, 0, and we're supposed to find an equation. So if you're given the vertex, which form of a quadratic function do you want to use? Vertex form, the one that has the vertex in it. So let's just start by writing that out. So this is very similar to when you try to find the equation of a line. You know, they say find the equation of a line that goes through this point and is perpendicular to this line, or they give you some properties, right? So now I'm giving you some properties, and I want you to find the equation of a parabola. So you start by writing out the general form. The first thing you would do if it was a line is you would write y equals mx plus b. So here you write y equals a times x minus h squared plus k. Then you put in the stuff you know. I know h and k. So I'm going to replace that h with a -2. So I always write the minus sign, x minus, and then you replace h with the -2. And then k is a 3, so I'm going to replace the k with a 3. Okay. So given that this parabola opens down, what do you know about the value of a? It's got to be negative, right? Because the negative is what does a reflection over the y-axis that would cause it to open down. So how could I find out exactly what it is? I know it's negative. Set y to 0, and what would I set x to? Let me just remind you, when we do a line, if I say, you know, slope 2 and through the point 1, 0, right? Then you would start by going y equals mx plus b. Oh, put in what I know. I know m. I have to figure out one more piece of information. I need to know b. How do I get it? I plug in the point, right? This is an x comma y. So I replace the x with a 1 and the y with a 0, and I solve for b, and I get -2. Okay. So my final formula will be y equals 2x minus 2. I do the same thing here. I start with my general form. I plug in what I know. I'm still missing one piece of information. I need to know what this a is. So I use my point. It goes through the point 1, 0. I make x1 and y0, solve for a. So 1 plus 2, that's 3, squared is 9. So I have 9a plus 3 equals 0. Subtract 3 from both sides and divide both sides by 9, and I get a is -1/3. And it came out negative just like I knew it should, right? Because it opens down. So parabolas can either look like this or like this. This is opens up, this is opens down. Nope, so then what I do is the same like when I'm doing a line, I have to take the a and put it in to write the equation. So my final equation, replace that a with a -1/3. And I've got my equation. All right, so I'm going to have you try one. Here's a graph. I gave you the vertex and a couple of other points. See if you can find an equation for this parabola. Okay. So I write down the vertex form, and I'm going to replace the vertex with its coordinates 3 and 5. So I replace the h with a 3 and the k with a 5. So y equals a times x minus 3 squared plus 5. Now there's just one piece of information missing, the a. If I knew the a, I'd be done. So to figure out what a is, I take either of my 2 points, doesn't matter which one, plug in the x coordinate for x and the y coordinate for y, and that will leave me with an equation where a is the only thing I don't know, and I can solve for a. So let's see, if I plug in 23 for y and 6 for x, so I'm plugging in this point here. Now I just want to solve for a. It's the only thing I don't know in that equation. So 6 minus 3 is 3, squared is 9. So I have 9a plus 5 equals 23. And then just solve for a. Subtract 5 from both sides, divide both sides by 9, and I get a equals 2. So my final equation is this one, but replace the a with a 2. Y equals 2 times x minus 3 squared plus 5. Good? Questions? All right. Okay, so now we have one given in the general form, the form that we're used to, ax squared plus bx plus c, and we're supposed to change it to standard form. So maybe it would help if I just write down standard form, so that way I'll know exactly what I need to figure out. So here's my standard form. I need to know a, h, and k. A I get for free because a in the 2 forms is the same number, right? So what is a? 5. So I have y equals 5 times x minus h squared plus k. And now I just need to know h and k. How do I figure them out? Negative b over 2a, yeah. H, the x coordinate of your vertex, is negative b over 2a. So I get 30 over 2 times 5, which is 3. So once I have an x, how do I find the y that corresponds to it? Plug it into the formula. So k is f of 3. So I take that 3 and I plug it in, and I'm going to get 9 times 5 is 45, minus 90 is negative 45, plus 49 is 4. So I now know h and k. So I can write out my final formula, y equals 5 times x minus 3 squared plus 4. How could I check and see if I did this right? Yeah, I could plug in an x here and plug in an x into this one, plug in an x into this one, and see if they give me the same y. That's a quick check I could do. So if I plug in x equals 0, I get negative 3 squared, which is 9, times 5 is 45, plus 4 is 49. And if I plug 0 in here, I also get y equals 49. So that's one quick thing I could do to check. What else could I do? I could simplify this guy. I could multiply out x minus 3 squared, distribute the 5, add the 4. y equals 5. When I square x minus 3, I get x squared minus 6x plus 9. And then if I distribute the 5, I get 5x squared minus 30x plus 45 plus 4. And that combine like terms, and I get 5x squared minus 30x plus 49, which is the equation I started with, formula I started with. Okay, so now I want to sketch it. So if I have it in vertex form, I can put its vertex down. My vertex is at 3, 4. So I'll sketch that immediately. 3, 4 is about right there. And then a couple more points is really all I need. I know its Y-intercept is what? Nope. 49. Look at the other equation, the constant on the end of the standard equation. The general equation is the Y-intercept. So if 0, 49 is on the graph, parabolas are symmetric. They have a line of symmetry. So if 0, 49 is on the graph, that's 3 to the left of the vertex. If I go 3 to the right of the vertex, 6, 49 should also be on the graph. And then we can just connect these. Make a parabola. So 3 points is all you really need to draw a pretty accurate sketch of a parabola. The vertex and 2 more points. What's the minimum value of this function? You got it. Good. That's the y coordinate of the minimum point. Good. Okay, so we're going to talk a little bit about area, because when we first learned about quadratics and quadratic equations, area was one of the times where you often see a quadratic equation pop up. So we have a farmer that has 400 feet of fencing to enclose a rectangular corral. To save money and fencing, he wants to use the bank of a river as one boundary of the corral because his cows or whatever can't cross the river. So what dimensions would enclose the largest area? So let's draw a little picture. We have a river. And then he's going to fence some area along the river. And he's not going to put fencing at the river because the cows can't cross anyway. So this is rectangular, which means that these two are going to have the same length, and this is going to have some other length. So what would the area of this corral be? Say it again. XY. Great, thanks. Area is length times width, x times y. And how much fencing? He had 400 feet? 400 meters? Nope, feet. 400 feet of fencing. So that means that when I add up all the fencing that he used, x plus y plus x, I should get 400. So 2x plus y gives me 400. And then the question asks me about maximizing area, right? It says, what are the dimensions? What should I make x and y to make the largest area corral? So this is a formula for area, but unfortunately, it's got 2 variables in it. We really are used to working with formulas that just have the 1 variable, functions that have 1 variable. So I use this other piece of information, right? And I can solve for one of my variables. So I would get y is 400 minus 2x. And then I could make a substitution into my area formula. So area is going to be x times, instead of y, put 400 minus 2x. So the area of my corral is a function of the lengths of one of the sides. And I want to find out what should I make x to make that area the biggest possible. So let's distribute the x, and I get negative 2x squared plus 400x plus 0, just so that we can put it in that general form that we're used to, ax squared plus bx plus c. Well, let's take a quick look at the graph of this thing. Negative 2x squared plus 400x. Now for a window, what's the smallest we would make x? Well, think about what it's representing. It's the length of a side of a corral, right? 100? Sure. And then what's the biggest I could make it? 400. I mean, you actually can't make it 400, but that's a good upper bound. And then for y, that's representing the area of the corral. So the smallest would be 0, you know, if I didn't build one. And then what would a really big area be? 500? That would be, not sure that that would be big enough. Because if we look at the corral, if I made this, say, 100, 100, and 200 to add up to 400, then my area would be 100 times 200, which is what? 100 times 200 is 20,000? 20,000? So let's just do like maybe 30,000. Oops. And I'll fix it if it's not a good guess. Okay, so I have a parabola opening downwards. I'm just not seeing the other half of it because negative x's aren't part of our domain. So I need to know, let me take a picture of this so I can draw on it. Okay, so this is x, the length of one side of the corral, and this is area. Y is area. So the maximum area is happening right here. Maybe I want to look a little further left, right? I'm not sure that that's the very top. So let's go to my window. Let's make the x min 0. That's better. Now I can see the whole parabola. So again, this is the x. The x coordinate is representing one length of the corral, and the y axis is representing area. So I'm interested in this point here because that is going to be the biggest area, and I want to know what x value will give me that. So there's two things I could do. I could have the calculator find it for me. That's pretty easy. Just do second, calculate maximum. Whoops. And it turns out that that point is at 100, 20,000. But let's pretend you forgot your calculator this day, right? How could I find out the coordinates of that point without using the maximum command of my calculator? Yeah, how do you find the vertex? You just told me. You answered last time I asked. Negative b over 2a. My vertex, the x coordinate of my vertex would be at negative 400 over 2 times negative 2. That's negative 400 over negative 4, which is 100, which is what the calculator gave. So, okay, we're good. And then k, the y-coordinate of the vertex, is just the area when x is 100. So if I plug a 100 in here, I'll just tell you, you get 20,000. Check. So to answer the question, they said, what dimensions should I build the corral to make the maximum area? X should be 100. What should Y be? 200. This should be 100. This should be 100. And I have 400 feet of fencing total, so this means this has to be 200. And then my area would be 20,000. So this is the answer to the question. All right, so the rest of class, I'm going to have you work in your groups on this penny drop activity. Another example of quadratic functions in real life.